In this chapter, we're studying the behavior of light. We're talking about reflection, refraction, interference, and diffraction. In this video, we're going to talk about the math that is involved with refraction. So we need to introduce a few new terms. The first is a term called the index of refraction. What that means is it gives the ability of a material to bend light. So the bigger the index of refraction, the greater its ability to bend light is. The symbol for index of refraction is a lowercase n. Sometimes you'll hear it called optical density. I'm going to give you two equations for the index of refraction. The first one is really the most practical. You'll see this one the most. So the index of refraction is the ratio between the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second, always, 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 and it's between that and the speed of light in whatever the second medium is. So kind of an interesting thing about the index of refraction is that it will not have any units because you have speed on top, speed on bottom, so the units are going to cancel out. Another way that you can look at it is because when you're talking about light changing mediums, the frequency of that light is the same. That means that the wavelength and the speed of the wave are actually going to be directly proportional. So if you want to, you can look at the index of refraction as a ratio between the wavelengths in a vacuum and the second medium, and you'll get the same number as you would in the first equation. However, 9 times out of 10, it's the first equation that you'll be dealing with, but I want you to be aware that you may occasionally see that second equation. When you're using the index of refraction in a problem, they'll either give it to you and have you solve for something else, or you'll be solving for that number. So you're never expected to memorize an index of refraction for any particular material, but I wanted to let you see this table of a bunch of different indexes of refraction so that you know kind of the range of numbers that you should be looking at when you solve a problem. So looking at this chart, if you were to do a math problem and get an answer of like 3,000, then that would give you a clue that you did something wrong. So it's always a really small number, usually between 1 and 2. You see diamonds a bit higher and silicon is much higher, but normally the numbers are 1 point something. Now, by definition, because we said the index of refraction is C over V, if we said the index of refraction for a vacuum would be the speed of light over itself, so that's why it's exactly 1. You notice that the speed of light in air is almost exactly 1. So when we do problem solving, we don't use that, the 5th decimal place for that number. You usually use 1 for that, even though technically a vacuum does have a lower index of refraction. Air at STP is about the same, and STP, if you don't remember from chemistry, is standard temperature and pressure. We don't do anything with that in this class, but that's just something that you should remember from chemistry. So you can see the other numbers, they're getting increasingly larger. Problems like to use diamond a lot, so you'll see that occasionally as well. And it's good to notice that the faster medium is going to have the smaller index of refraction. So 1 is the smallest index of refraction that you can have, and also the fastest medium. So you can be aware of that when you're problem solving as well. I'm going to do a quick qualitative example of index of refraction, and you'll see this on your homework, which is why I kind of threw this qualitative one in with all the quantitative stuff we're talking about. But then I'll do some quantitative things as well. So the first one here, we've got, say we have like a bucket of water. So there's my bucket of water. And in this bucket of water, I've placed a rod. So that's the actual location of the rod. And then we're going to insert a creepy eyeball. So there's creepy eyeball. And the eyeball is just going to be looking at the rod. The question is, why do you, when you look into the water, why do things appear to be at a slightly different location than they actually are? And the answer for that, as you probably know from our class discussion so far, is because of the refraction of light. But let's take a look at how this works in this particular situation. So the best way to look at this, I think, is to trace a ray. So we're going to start at one spot on the bar, and I chose the very bottom of the bar. You could do this for any place along the bar, but I think the end of it makes the most sense. And we're going to take a ray and trace it back to the eyeball. And you could do this a number of ways, but I made it one way here that we can look at it. I chose an angle, so there's no particular direction to this particular ray that I chose. Since it's qualitative, we don't know any real angles that are involved. But let's say a ray of light has bounced down to the bottom of the rod and is reflected back to the water. So currently normally the ray is traveling from the water to the air. We know that air is a faster medium than the water, so we're going from slow to fast. So just like all of those ray diagrams we did earlier, we can construct a diagram like this and see which way it's going to bend. So we're going from slow to fast, so that means we're going to bend away from the normal. Remember, that's Fran. Faster refracts away from normal, and that means into faster refracts away from normal. So your eye doesn't know that the light has bent. When the bright light ray comes to your eye assumes that it's coming at it straight the whole way. It can't follow a bend that happened at some point earlier. So where are you going to see that rod? If you trace back that light ray, you would see the end of that rod there where the purple arrow is pointed. So if I wanted to see how the rod appeared to be bent, I'm going to start here where the rod first touches the water and end over here where my eye would see the end of the rod. And if I connect those two, that would be how the rod appears to be bent inside the tub of water. So that's the qualitative look at how an index of refraction is going to affect light rays as they go through the air. So here's a quick sample problem on index of refraction, and this is a pretty easy one, but you'll see problems like this, so I want to make sure that you know how they work. So here they give you the speed of light in glass is 2 times 10 to the 8th meters per second. What is the index of refraction? By the way, if you see the speed of light in glass and it's a different number, don't panic, because there's a lot of different kinds of glass, and different types of glass are going to have different speeds of light. So there could be a number of different values used for that. So in this case, they're giving us the speed of light in glass. We want to know the index of refraction. So I went ahead and wrote my knowns and unknowns. You may not need to do that on a problem this simple, but just to make sure we dot our I's and cross our T's, we've got the speed of light in the glass, and we've got the speed of light in a vacuum, and we're looking for n. So our equation is the one that we looked at earlier. Index of refraction equals the speed of light in a vacuum divided by the speed of light in the glass. They will never give you c, by the way. Since it's a constant, it's something that you're expected to know. So here's my solution. I take the 3 times 10 to the 8th divided by the 2 times 10 to the 8th, and I get 1.5. Notice again that there are no units on this value.